the weight input alignment works. So as the B parameter is increased, the cosine power highs, and it tries to align the weights and inputs which are really relevant to a specific problem. So on a very high level, just remember this for now. Second part, so this is, yeah, that's what it's called, the align pressure. And in the second part, like how these models are shown to be faithful, again, like there is a concept which is called dynamic linearity, which is basically the output could be represented as the multiplication between the linear transform or the dynamic linear transform, which is input dependent, times the input. What does that mean? So given an input, you can simply take a cross product with the explanation, and you would literally get the value of the logic. And this is called dynamically linear because during inference, you could literally treat it as a piecewise linear function and calculate these explanations. So the whole model becomes a single linear transform, which could be summarized. So you could just get the output by multiplying these weight vectors, dynamic linear transforms into input, and you would get the logic scores. So on a very high level, like these are the two things just to remember, like how, because we'll see, like we also play with the B parameter to have a good explanations, and it's important to just have a quick idea. But definitely I would recommend to check out the paper. Okay, so now now we know, like on a very high level, how BCOS works, and we have an idea how the standard models usually are. So I would, in this first part, would take an example of a ResNet 18 architecture, because that's the simplest convolution model is there, and I'll one by one, step by step, try to explain and show like which different components made sense for us and how we brought interpretability to it. So let's talk about how the standard models and BCOS models differ. So in general, the standard model has 3 input channel, while the BCOS model takes a 6 input channel. And why is that the case? Because the 6 input channel enables it to have a colored explanation, which is unique for each input pixel. Similarly, like the standard models have convolution layers. The BCOS model use a BCOS convolution layer, which is again like is the same transform as we discussed before, but the B power is raised higher for a higher alignment pressure. Standard model use batch norm. BCOS use something, it's same, but it's use batch norm uncentered, where they don't subtract the mean, and then they saw like because of the model faithfulness, it's required to do in such a way. Standard model uses activation layers such as ReLU, but in the BCOS model, it has shown that it doesn't require any activation. And they also have some ablations later on to show that, okay, you can also use something called max out activation, which is a generalization of ReLU, and it still works, which also we incorporate in our work. Further, standard models use max pool, but BCOS has average pool. And similarly, in these different layers have these changes accordingly. In the end, when you have this average pooling layer and a final linear layer, but in the BCOS model, they reverse this order, and then they use 1x1 convolution before doing the average pool. The reason behind that, when you do average pool and then you pass it through a fully connected linear layer, then the focus of the features get convoluted because of the average pooling before. So what they figured out is, like before, if you just do a 1x1 convolution, and then when you have features again like aligned, and then do an average pool, that is much better. And also they use something logic layer, which is again very specific to BCOS model, because they are trained in such a way using binary cross entropy laws that the output features are kind of pushed, the negative features are pushed negatively and the positive is pushed positively. So they, to balance that thing out, a logic layer is required, which adds the logic bias in the end for the outputs. And standard models have biases, but BCOS doesn't use no biases because of faithfulness. And as I mentioned before, that BCOS does this weight normalization, but standard models just have normal weights. And definitely the standard models have the pre-trained weights that we leverage, and the BCOS models are trained from scratch, which means that they have randomly initialized weights. So the question here is that we see that there are so many differences between a standard model and a BCOS model. So how to bridge this gap is the real question. So what we want to do is that, given a standard model, we see it's already highly performant, and a B-cosified model, which would be also performing same, and it would be a functionally equivalent model if I just have b equal to 1. So as I said before, like the b-cos transformation here, if you just said b equal to 1, it's literally the linear transformation in a standard model. So in this case, at the very first step, we just want to replace these linear layers with b-cos layers, but with b equal to 1. So we still have a functionally equivalent model. But now, given you have a b-cos layer there, it gives you a chance to get the explanations. So on the second step, what we want to do is that given these explanations with b equal to 1 won't be really good because you don't have alignment pressure yet, we want to increase this b to a higher power, and then we want to get better explanations of this functionally equivalent model. And that's these two steps combined is what we in the second part do the B-cosification process. So again, let's look now into more detail. So this were the differences and like how we tackle each differences one at a time. So again, starting with the example of a standard ResNet 18 model here. How do we bridge this gap and add these changes? So again, we want to first achieve the functional equivalence where both the models should perform same. We don't want to lose any performance there. And for that, like we just replace the convolution and the linear layers with the B-cos transform layers. And at b equal to 1, as mentioned, again, it's a equivalent model. Further, we also saw that the ReLUs are compatible and are in distribution to the standard layers, and we saw that we could use it. And as in the previous B-cos models, it's also shown that you could use a generalized version of ReLU, which is a maxout, as I mentioned here. And it has also shown to be compatible, so we also keep it because in this way, the weights are really in distribution. Further, we don't use any weight normalizations as a standard model. Again, the reason being we want the weights to be still in distribution when we further fine-tune them. And again, like we discussed like how it makes sense to still have no weight normalization as opposed to what was mentioned in the B-cos original paper, that when you have a batch norm followed by a B-cos layer, it becomes just a scaling factor. But I mean, for now, let's not go into that detail, but the whole idea is, again, like to have these weights in distribution. And in the end, definitely we want the pre-trained weights to be used. And again, like the model at this point is again equivalent and the weights are in distribution. So with these changes, we achieve the functional equivalence for a B-cosified model. Once we have achieved this functional equivalence, so now you have the same performance, and now explanations are still not good. We want to now go more closer to a B-cos model and have more better explanations. So for that, the very first step, again, like as in the standard model, we use 3-channel input, but the B-cos has a 6-channel input because of the colored explanations. We want to change that factor, but at the same time, it should be in an equivalent way. So we want to have these colored explanations. And how do we do it? Like we find an equivalent transformation to transform the 3-input channel into a 6-input channel. Basically, we add additional 3 channels to the input, which is 1 minus R1 minus G1 minus B with RGB channels. And we found that this kind of equivalent transformation normalization could be used on top of the given inputs, and you would end up with a equivalent normalized version of the inputs for 6-channel. And similarly, we update the weight matrix because now you have the input rather than 3-channel input, you have 6 channels. So you can have an identical output weight matrix, which can be derived like this. So at the very first step, now we are able to bridge one of the gaps where you could now have a colored explanation for a functionally equivalent model. So, and at this step, we see that the pre-trained accuracy is preserved. So we know like the changes which we did to the model are still preserving the original accuracy and the model is functionally equivalent. Now, further, we want to go from here towards the B-cos side because we want explanations again. So the very first step is like definitely we increase B to a higher value where we want to have this input weight alignment pressure. And then when the weights and inputs are aligned, we hope that the explanations for specific logics or where it should really focus, it would increase. And that's what we do as done also in the BCOS. Then the second part is that we want to decay the biases for the faithfulness, because the standard model has biases. And for the faithful explanations, because doesn't use any biases, but we also want to decay it in different ways that we'll discuss, like how we differently decay these biases. And then further, there are, so at this point, you can already see the explanations get better, but definitely to improve them. And so yeah, for example, here you could see like for this specific set of transformations, the explanations over the epochs already, when you fine tune this model, it starts getting better. And why we I also didn't mention, like you still need to fine tune, because after functional equivalence, when you add BCOS layer with higher power, it again, like the pre-trained weights need to adapt to this change because it's not functionally equivalent anymore. So you fine tune a bit, but you see like over the epochs, it just improves. So further, to have these explanations even better, what we also adapted from the original BCOS model is that we also use the batch norm uncentered as they use for more faithful explanations. We also try to have this global average pooling order, as discussed before. We want to have the features to be focused more and then do the pooling. And additionally, we add the logic layer because we also use the same training setup from the BCOS. We also use the binary cross entropy loss to have this training setup. So, and yeah, at the stem, we also replace the max pool with the average pool, again, similar to a BCOS model. Yeah, so at this point, now we have this completely new model, which is we call a B-cosified model, which has the same performance benefits from standard, but also we incorporate the changes from the BCOS so that you have a better explanations. So this is very specific, like again, like here we use the ResNet 18 architecture, but for VIT models, you also have to take care of how the GALU and the attention pooling done, but we do it in a similar way. So at this point, we have this B-cosified ResNet model. And what we here did in summary is that we started with the conventional deep neural network, which here you could see has explanation from a post hoc method, which is not interpretable and often not faithful. So first, we want to convert it into a functionally equivalent BCOS-like deep neural network, which has identical accuracy, shows explanations in color. But at this point, as you could expect, like the interpretability is poor because we don't have any alignment pressure. So in the second step, we fine tune it and change the linear layers, the BCOS transformed layers to a higher power. And then at this point, we can already fine tune this model to adapt to these changes. And we see that the accuracy quickly recovers for different architectures. And now you could see the explanations in color. And these are interpretable like original BCOS models. So again, like on a level of summary, you could think, you can see how we did this process. So let's jump into one more detailed level. So how we achieve each specific part specifically on the fine tuning side, because functional equivalent, you just do the changes and you can reach there. But for the fine tuning, how do you change the B parameter and how do you decay the biases was another question to explore. So for that, what we did is for the experimental setup, we qualitatively looked at the colored explanations that definitely they should improve when we do these this fine tuning process after the functional equivalence. And we also looked at the raw attributions, which shows like what positive contributions are for a specific class, where the blue shows the negative contributions. And quantitatively, definitely, we look at the performance should match to a standard model, and we evaluated on ImageNet for the top one accuracy. In terms of the quantitative analysis of this explanations, we use something called grid PG scores, which was also used in the original BCOS models. So what happens here is that the model is trained on individual images from ImageNet. So for example, here you see a grid of 2x2 from the images from the ImageNet. And each image is a separate image from ImageNet on which the model is trained. But what we want is that let's say if I say the ice cream, the model should be able to highlight what exactly the ice cream is in the grid image, because it's synthetically generated. It never saw it, but it knows like what are the relevant features for it to be called an ice cream. So it should be able to evaluate it. And to quantify this, what we do is that we take the score of the attributions that are given to that specific class that we are targeting over the overall attributions which is given to the whole grid. And this is what is called the grid PG scores. Yeah. So yeah, then moving on. So these are the evaluation metrics. Now let's see like how did we use them to come up with how we should increase the B for increasing the weight input alignment, and how we could decay the bias. So first, talking about increasing the B in these B-cos transforms. So again, like we take this resonate 18 example, and we have these are metrics of accuracy and localization, which is the grid PG scores again. So here the baselines for a standard model. Here you could see what is the accuracy and the localization score, and also for the B-cos model. And here you could clearly see the localization scores for standard model, as we would expect, is low, because it's not really interpretable. So how we set B is like we first try to set it in a discrete way, which is we can directly set B to some value and see like how the model performed to these changes. So for example, you could set B directly to any of these values or whatever value you think of. So we tried out these different values. And for example, here we see that setting to these, so at B equal to 1, again, the model is functionally equivalent. Remember that. So here again, the localization scores are not great, but as soon as you increase B, the localization scores increase. And also we are able to have even better accuracy because we fine tune it further. So yeah, like you can increase B and see these performance gains. And here again, like for these different values of B, how the localization metric also looks like, just to give an idea. So I think like after B equal to 2, and we already see that this interpretability score does not really change. So in that way, I think it's already good. You can see the trade-off between the values. And also in terms of the explanations, here you could see how the explanation changes as you increase more alignment pressure using this B parameter. So yeah, so in this case, we could see like definitely increasing the B is helping, and you could set B to a higher value. And then another idea was that we could change this B linearly, because it's possible that when you set B directly to a higher value, let's say B equal to 2, that you would disrupt the weights. And so here the linear B idea was that you slowly increase B to some higher value over the whole fine-tuning process. So for example, you could change B, let's say in 5 epochs from 1 to 2, or over the whole training epochs. Here we use 90 epochs, changing it from 1 to 2. Yeah. So again, here we see like in these different number of epochs, how the model performs. So we could clearly see that even in 5 epochs, the model is able to have a good localization score as well as accuracy, and like as compared to the other number of epochs as we change B. So there was not really a clear benefit to just let it change over the epochs. And then also we also try to let the B parameter to be learnable and see like what model decides. So here again, we see that the accuracy and the localization scores are very close to all the other methods. So what we stick to is the very simple and basic, where you could just simply set B equal to 2, and it gives us the performance which is on par with other methods, and also the localization scores. And here you could see the examples of explanations for different images again. When you set B equal to 2, how it looks. So that was the part on how we increase B. Now let's talk about how we decrease the biases. So in a similar way, let's keep this example of resonate 18 with accuracy and localization. We have the baseline scores for both of them, the standard and the B-cos model. So again, like in a fixed bias way, we could either remove all the biases, how it works. So here you see this column with no biases. And we also definitely compared if you keep the biases, what happens. So here you could see that the localization scores again are not really interpretable because the model cannot give faithful explanations. So yeah, so with biases and also the explanations look like this. But when you don't use any biases, then model gives good explanations and able to retain this accuracy. Further, we also try to decay this bias similarly using weight. It is able to learn how to decay the weights over the training. And with different decay parameters here, you can again see how the explanations look. Again, like it's again like a trade-off where you either let a model try to learn and it increases the whole computational, stick to very simple method where we just remove all the biases, and it again like gives the performance which is on par with other methods, and explanations look good in terms of qualitatively and quantitatively. Then further we operate aberrations, because as I mentioned before that you have this increasing B and decreasing biases, but there are also components that we switch from B-cos to a standard model. So we saw like how they affect the overall architecture. So again, like for this, I'll show the comparison with the accuracy localization scores and how the explanation changed with these different ablated components. And here you see the explanation of a B-cosified ResNet 18 model that we have. Now, suppose first you have ablation over a batch norm. So as I mentioned before, the B-cos uses batch norm uncentered, but rather if we use batch norm, what happens? So we saw like if we have a batch norm uncentered, we see clearly a localization scores have a major bump, and also the accuracy improves. And we could also see like if we don't use this, how the explanations would look like. Similarly, how the order of this global average pooling affects. Again, we see that the localization scores improve. Also for the ReLU activation, if we don't use it, how the explanations look, and how using it improves the localization scores and accuracy. With the logit bias, again, like here we see that localization scores drop, but although we could clearly see that there are some negative contributions which also come into play. So that's why it's better to use them. And similarly on the average pooling, we also kept it similar, because here if you look that clearly the explanations look much clearer. So overall, that's how we did different ablations and all these different strategies with increasing B and decreasing the biases. We came up with this framework which we call B-cosification. We are given a standard model, which again, like you could represent at B equal to 1 in a functional equivalent case. And given the pre-trained weights, we increase the B and we decrease the biases, and we could clearly see how we have these explanation changing from a standard model, which is not interpretable, to a interpretable B-cosified model. So that was the first part where we have where I give you idea of how we B-cosify the let's say. So here we have this example of ResNet 18 model, but in a similar strategy you could also B-cosify other conventional pre-trained models, and we see that the models are performant, had good explanations, and we did in a cost-effective way, which I'll show further in the results, like how we had these different speed ups. So let's talk about the second part. Here I'll show like how we bring the explainability to these supervised vision models, specifically to the convolution and the VIT vision transformers, and how we leverage the weights and do this transfer of the weights where the standard explanations get similar to a B-cos explanation in a B-cosified way. So for these, so once you have B-cosified the model, now we extend this framework to different convolution, different conventional models, and we want to see like how they perform. So for this, how we do the evaluation? Again, we use ImageNet dataset for having the top one accuracy, and we tested it on different models, specifically as mentioned here on ResNet 18, 50, and DenseNet 1-to-1, and for different vision transformers of different sizes like tiny, small, base, large. And we also see like with and without convolution stem how these different models look. And we fine tune for 90 epochs as it's done similar in a standard case or in a B-cos model. So in terms of accuracy, so these are the different models here I mentioned. So again, these different models, the convolution and VIT, and these are like the pre-trained accuracy of these models, like what is the pre-trained conventional scores. And this is the BCOS, original BCOS models, which are trained from scratch. For them, the top one accuracy on ImageNet. And this is what we achieve with the B-cosified model. And here we could clearly see like this is the change between the accuracy of a BCOS and a B-cosified model. And we clearly see that training from scratch in a BCOS model is not really beneficial compared to if you just B-cosify conventional model and then fine tune them. So here you could see like for most of the models that we are able to achieve better accuracies. Also in terms of efficiency gains, that here where I mentioned T is the at the epoch at which the B-cosified model was already at the accuracy of a final BCOS model trained from scratch. So for example, here you could see like in 29 epochs, the B-cosified ResNet 18 was already at the final accuracy of a BCOS model. So we could see that there is 3.1 times gains in speed up, and it goes up to 9 times speed up in some of the cases. So which is already good. Rather than training from scratch, you can have better efficiency gains in such a way. In terms of the interpretability, again, we use the localization scores that are the grid PG scores we saw before. So this is the comparison of different models, different convolution models and the VIT models. And to just give you a quick summary of this. So again, like it uses a grid image here, for example, 3x3 grid. And if you want to look at a specific explanation for, I don't know what's the label of this, but let's say bottles. For the standard model here, you could see how the input time gradients explanation look for this, which is represented here in the yellow. And it is compared with the B-cosified, which is a green one, and it's on par with the in terms of localization scores and also in terms of how it looks to a original B-cos model. So again, like we are able to have similar interpretability here. And again, it translates to other models, as you could see in the plot. We also did this comparison with different post hoc methods which are there. So for example, in the previous slide, I showed here the input time gradient, but we also compare it with different methods which are already there, which you can post hoc apply to the given conventional models. And for example, here for ResNet 50, you could clearly see that the green one is the B-cosified model, is able to have really good scores compared to the other models which perform on this grid PG scores. And similarly for other models, we could see, for example, again here for the DenseNet case. So yeah, and now let's talk about the impact of pre-trained weights, like how different types of pre-trained weights impacts this B-cosification process. So again, like we have this B-cosified model here. Here we talk about the B-cosified ResNet 50 now. And the BCOS ResNet 50, which is a standard one, which is again trained from in a B-cosification recipe, achieves this localization and accuracy scores. And now we want to compare it like, okay, what happens like if you have trained a, I don't know, ResNet 50 with Dino style trained model. So here we try to have these different weight comparisons. So as a baseline, we have randomly initialized model and then we B-cosify and train it. Similarly, there are different training routines which are used for ResNet 50, which on Torch Vision it says V1 and V2. V2 is basically a longer training run. And similarly, Cliff are trained in a contrastive way, and Dino ResNet 50 is trained in a self-supervised way. So you have different training regimes, and then you have a same ResNet 50 model, which you could again B-cosify and see. So comparing here the accuracy again, like for these different weight initializations, you could see how different models achieve these scores when trained on a B-cosified model. And we could compare here with a standard BCOS model which was trained, and you could clearly see how what is the impact of different pre-trained weights. So with the randomly initialized, we would expect that it won't be able to have the same benefits. And again, the speed ups, we see that we are able to achieve these accuracies of a B-cos model in again, like with the speed ups of when you reach that epoch. So it's pretty clear that the different pre-trained weights can have different speed up impacts, and in terms of localization scores also, that all these different weights help. So clearly stronger pre-trained weights help to boost the performance, but we saw like if we just naively use the contrastive pre-trained weights from clip, it did not show any gains in the supervised training, which we suspect that because of the different training paradigms altogether. And that's why we don't really see much gains in terms of performance, although again, localizations are good. So that was the second part where we tried to extend this strategy that I discussed in the first part to these different architectures, and how we saw like how the accuracy and the localization scores, which evaluate the interpretability, look for these new B-cosified models. Then after this, then we went one step further, and we wanted to extend this idea to the foundation models, which was the goal, one of the goals, because now again, as discussed, like these models are training from scratch is really costly. So how we could B-cosify now these existing clip models, and we, again, the goal is that we achieve similar performance, zero shot generalization, and we are able to explain it with text. So a standard clip model, which does a contrastive training, has two parts, which is one is the image encoder and a text encoder, where these are in a contrastive pre-training manner it is trained. And for the evaluation, what happens is, again, like you have data set from different labeled text, and then you have a text encoder. And when you want to do a zero shot prediction, you take this pre-trained clip encoder, and then you try to maximize which text aligns most with this image, and then you get, let's say it's a photo of a box. Okay, but in our case, let's first talk about the first part, which is training, and the second, evaluation, how we do the evaluation. So in terms of the training of a B-cosified clip model, what we had to do is that we first take a image encoder. Here, let's say we use the clip ResNet 50 model. We B-cosify it. So as discussed in the first part, like you could B-cosify a ResNet or any other model. So we similarly B-cosify this pre-trained clip ResNet 50 model. Then for the text encoder part, we don't use any text encoder. Rather, we use a frozen clip image encoder itself, because the reason given that we don't need any text encoder, and we do it so that we have some kind of a feature alignment training. So here the goal is that when you have B-cosified the image encoder, you want to have it close to what standard clip would have performed. So you want to keep this zero shot generalization, and as it's B-cosified, you would expect that it also has these explanation benefits. So in that way, we do a feature alignment training where you don't need any text encoder for training. Rather, we use a clip image encoder, which is frozen, and we just fine tune the B-cosified image encoder, and we do this feature alignment training on the same set of data. Also, we in the experiments we saw that rather than using a standard clip loss, the sigmoid siglip loss seemed to perform good, which gave us additional benefits in terms of the performance and explanations as well. And then further on the second part of evaluation, again, how do we do it in our case? We have this image encoder, which we fine tune in the first step or train in the first step. So we have this B-cosified image encoder, which is frozen. And for the text encoder, we use a frozen clip text encoder from a standard clip. And now, again, in the same way, you could pass a text prompt and give in the image. And now at this point, you can get the zero shot generalization or the score from this, like what image is this, or like it's a photo of a fox. But additionally, you could also get these explanations now, because now you're using a B-cosified image encoder. So that ideally also highlights for you, like, okay, where's the fox in the image? So in terms of, so this was the process of the how we trained it and how then we evaluated it. In terms of results, specifically for the accuracy, I'll discuss here like what is the experimental setup we use. Again, we have this clip ResNet 50, which is trained under the same B-cosification recipe. For the baseline, we compare it with something called text to concept. This on a very high level. Here, what the aim is that you could attach a linear layer on any kind of model, and you can align the weights it to mimic as some other model. So here, for example, we take the BCOS resonant 50, the original one, we attach a linear layer on top of it, and we try to do it alignment with a clip image encoder so that the model gets the same advantage as a clip, or the features get aligned more towards a clip image encoder. So that's why it's like now you can have output that would mimic the output of a clip image encoder, but you also use the BCOS encoder, so you could have explanation. So this was kind of a comparison that we wanted to see, like if you just add a simple alignment layer on top of a BCOS, original BCOS model, how does it perform compared to the strategy we showed in terms of B-cosification. For the B-cosified models, we fine-tuned definitely on ImageNet, and we also tested on a larger data set, which is CC3M, which contains different captions and images. Again, we don't use any text for our training, so yeah, that's but it has a different, it was a bigger data set and has more distribution to it. And then definitely we compare these scores with the standard clip, which is the again like another model to compare. So in terms of zero-shot evaluation, how we see is that on different categories of data sets, so for example, here the natural data set is what very similar to on which the original, the ImageNet distribution is based. So here you could see like how these different models perform, and we could clearly see that it's clearly better than the text to concept baseline, but also it performs pretty similar to the standard clip, which is trained in like trained on a very large data set, but we are still able to have this on par performance. Similarly, on different kinds of data set, we also saw that different B-cosified models can still perform better with the baseline and have close performance to a standard clip model. And also like, again, these different categories where you have more structured data, let's say MNIST, where you have different kind of structures in the image, like how the B-cosified model again performs good. In terms of linear probe evaluation, we also try to add a linear probe on top of these different image encoder, and we saw again similar results translate to a linear probe setting as well, that the model performs good in these different data categories. Now again, like having to evaluate how now in terms of interpretability the model performs. So for this, how do we do the interpretability evaluation is on a Pascal VOC dataset, which is a multi-class dataset per image, and which provides the bounding box around different objects to indicate where is the object. And for the evaluation of such multi-class object dataset, we do the evaluation. Again, it's very similar as the grid PG scores, but here how you get the score is that for a given explanation, if you want to have score for how it should have focused on a cow, we take again the attribution scores that would lie in that bounding box compared to how the overall the attributions are in the image. So this is the evaluation metric, and here you could see the results for this EPG score. So the very first is the standard clip on the same evaluation scheme. And we also compare it with the GradCam, which is again a post hoc attribution method, which is commonly used to explain these models. And we compare it with the B-cosified model. So here we see that clearly it's better than the standard clip in terms of interpretability scores. And compared to a pre-trained model evaluated with the GradCam, that the B-cosified clip performs better, but although the gap is not really much. So in that case, we try to figure out how we could even have even better interpretable results, because here you could see the explanation for this specific class. The explanation seems to be pretty distributed for the cow, and you cannot really say like, okay, what the model is focusing on. So going one step further, then we try to look further into the B-cosified image encoder. So what's happening at the very last step is that you have some unpooled features that you get. And then these unpooled features is again pooled, and through which you get your scores. So again, this story is very similar to what happens in the convolution models, where we switch the order of the last average pooling or the global average pooling to have features focus first and then do the pooling. In a similar strategical way, what we do here is that we don't do the pooling here. We directly use the unpooled features. So now your output changes accordingly because you don't do pool. So for each feature, you have the outputs. And from the clip text encoder, so for example, we want to see like where's the cow in the image. What you have is now this output from this text encoder about the cow. And now what you could do is that you take the scores for this text encoding and these individual features. So on the individual feature side, like when you do the cosine between text and these individual features, we again raise this features to a higher power so that it is able to focus specifically on the cow. And then we pull these features. And when you see this, now the explanation is really able to focus on the cow here when you see these attributions. So it's like it's very similar to what the original BCOS shows the ideas, but here you could also have the explanations more improved when you try to do it on a feature level rather than having this pooling. And now in terms of the localization scores, so this is again the same scores as I showed in the previous one with the bar graph. Now it's represented as this line, the single line which represent each scores. But the more here now we increase the cosine power, again we see the same story that the scores improve. So the higher the power, the model is able to focus more on these features and the scores improve, and also the explanations. So yeah, and like here, more qualitative examples. So for example, what happens like if you have a standard case where you do the average pooling, but if you have each features to be focused with a higher power, what happens? Qualitatively, now comparison to a GradCam, here you could see these results. Now you could compare with more examples like how a standard GradCam gives you the scores for these different classes. But again, it's clear that how interpretable it is. And now this I find interesting, that now you could use the text to do different kind of localizations in different images. For example, like here, this is an input image, and now you can give a text prompt such as where is the nose. So the model would try to highlight the nose for you in the image, although again it's not perfect. But again, like having you can try to highlight different parts of the image, say ears or let's say eyes. So you could have these different explanations. Few more examples. So for example, now we have an ice cream here, and we want to definitely see where's the ice cream, but also I want to see where's the cherry or the cup or the heart shapes. Similarly, another example, you can ask like where's the water jug in this image, where's the hand or the girl or the boy. So accordingly, the model is able to focus on relevant features, which already gives an idea like how this model would work with a text input. Further, more examples, where's the ship or the fortress from the background, and the mountains or the water. You can also ask it like, okay, where's the green color in the image or the blue color? So it would focus now on the blue caps. And you could also see like it also in this raw attributions, what negatively it's focusing on, and trying to not highlight those in the colored explanations. Or the orange color, or overall the white, which I think it tried to highlights the ice part. Similarly, you can also give it an input of a grid image, and here you could do the same story. Surprisingly, it is able to also identify like how different ethnicities or diversity groups, like for example, you want to highlight black, white, Asian or Hispanic. So it's still able, again, like it's not perfect, or but it would still give you idea about the inherent biases of these different models, which could again be helpful for further research. or different hairstyles. So for example, having people having different curls or the braids, or just straight hair. So yeah, overall, in this way, we use this B-cosification strategy, where we first went from a conventional pre-trained model to a functionally equivalent model, and then we extended further to a vision language model. So that was like the overall overview with these three different parts. So in summary, we try to answer this question: can we bring inherent interpretability to these pre-trained deep neural networks, but in a cost-effective way? And we try to find the best strategy to B-cosify. We want to then, after finding the strategy, want to extend it to supervised models to bring explainability. And we want to extend it to vision language models as well. So we come up with a B-cosification framework where increasing B and decreasing biases could already give you performant models. Then we tested it out on different supervised models, such as here we did it on convolution and different vision transformers. And we are able to achieve performant, cost-effective, interpretable, and in a way, we could transfer these weights from the pre-trained models to a B-cosified model. And further, we extended to a clip model, and we use limited data such as ImageNet as compared to what it is originally trained on. And we had low training costs, and we were able to see how the model has zero-shot generalization, which is very close and on par with the standard models in terms of both zero-shot and linear probe. And the model is shown to be interpretable like BCOS clip now. And you could use the text to explain, definitely, as we saw in the examples. So overall, yeah, that was the gist or summary or the overall idea of the paper. And thank you so much for your attentions, and I'm open to any questions. And yeah, the paper and code is available on this links, so feel free to check it out.
Yep. Thanks a lot, Claire, for the presentation. I know firsthand how hard you worked on this paper, so it's super cool. And I think it's a thing that we talk about quite a lot in our efficiency group of like how efficiency is just not at the operation level or the hardware level, but also data and how that is.
To train from scratch, it's not really beneficial. So how could we bring the interpretability to the pre-trained models in a cheaper way? That's the real question that we want to answer. And can we leverage the pre-trained weights which are present in these models? And does it transfer? So that's the question that we want to ask, and that's how we come up with this method called B-cosification. And specifically for clip, we saw that we could have good zero-shot generalization, and also we could explain now using with text. I'll just give a brief overview, and then we'll go into detail of each of it. So we'll see how it works. So the key question that we want to answer here is that can we bring the inherent interpretability to these pre-trained deep neural networks, and also in a cost-effective way? So in our work, the B-cosification, given we have these conventional deep neural networks and a B-cos deep neural network, which gives inherent interpretable human explanations, how can we bridge this gap? So that's what we do in the B-cosification, where we want to fine-tune. We want to first transform and then fine-tune the models towards this interpretability. And we have seen that it performs on par with these conventional and the BCOS models, gives model faithful and human interpretable explanations, and can be used for foundation models where the training from scratch is costly. So specifically, for example, here, you can see here in the graph, I'll try to explain. So on the x-axis here, you could see the number of epochs on which a model is trained. And on the y-axis, you see the accuracy. So the orange curve shows the BCOS model, which is the original model trained from scratch, versus a B-cosified model. Then specifically here is the DenseNet model. And here you could see like in the 19 epochs, you're able to reach the accuracy which the BCOS model trained from scratch reaches in the 90 epochs. And it gives us the 4.7 times speed of where you would try to train these models from scratch compared to a B-cosified model. And we see that these results generalizes to different architectures. And also here, for example, we can see in the VIT models, it also gives us really good speed up benefits in the training. In terms of interpretability, here you could see that there are a few examples here from the ImageNet. The model provides a model faithful and human interpretable explanations in the BCOS case. But if you look at the conventional models, which is here in the third column, they're not really interpretable. If you try to do it again with some post-hoc attribution, and they look like this. But just after one epoch of fine-tuning using the B-cosification, we can see that these explanations are on par with what BCOS model shows. And also these persist over the whole fine-tuning process. So that really gives us a good idea that you could have these explanations, and you again have this trade-off where you can have a really good explanation of what is the reasoning behind it and also have a performing model. Similarly, we also saw that we can extend this to the foundation models, such as CLIP, where training from scratch again is costly. So you could B-cosify a CLIP model already, and you can have such benefits where given an input image and using a text now, you could really explain and see like what model stands in terms of when you say, okay, I want to see a picture of a dog in the image, and it highlights it for you, and that is again human interpretable. So this was like the overall gist of what we did in a very quick 2 minutes pitch. But let's now look what the overview of the whole talk would be today. So I'll discuss like how we find the best strategy to come up with this B-cosification, or how we B-cosify these conventional deep neural networks. And then once we have achieved this, how we bring the explainability to these supervised vision models. And in the end, we'll also discuss like how we extended it to the vision language model, specifically to the CLIP model. So for finding the best strategy to B-cosify, we saw that we wanted to have good performance. The explanations should look good, as it should look like a B-cos explanation, and it should be done in a cost-effective manner, because that's the whole point of this. And that's what we call B-cosification. Then in the second part, we'll see like how we extended it to different convolution and VIT architectures, and how we leverage these pre-trained weights from these pre-trained models which are already available, and does it transfer or not, like if we could already use this. And the goal is like moving from this conventional standard models to a B-cosified model, so you could have good performance as well as the explanations look great. And then in the end, we'll see like how we extended it to the vision language model, specifically for the CLIP. And we saw the zero-shot generalization there. And also, as I just showed the example of how you can explain the text, we'll see more how it can do a lot of things. We want, given an input image, to highlight what's there. Yeah, Harsha.
So I had a quick question. So the assumption is also here, like, to be able to reclassify something, that the sort of representations that we would make more explainable should already be present, right? Uh, is this typically a feature that comes from like having like from optimization choices, or is it coming from like these kind of training techniques we're using, the supervised, self-supervised? Or could you also elaborate on that? Because you mentioned like supervised vision models and vision language models were typically trained in semi or self-supervised. I hope that question makes sense.
Yeah.
It's like an assumption you're making that it's present, right?
Yeah, so we did some experiments, like for example, with self-supervised dyno models, and for the CLIP, like which are trained in contrastive, we'll see how it. But obviously, like I think our focus was more on the supervised models, on which like previously the BCOS models were also developed. But I'll show in the results, we have some ablations over how different training. How differently train these pre-trained models, for example, contrastive, self-supervised, how they perform in such a case if you try to B-cosify them. So I think like we'll see. But yeah, I think in general, the hope is, and assumption is, that it would transfer, and we to a point see that it does. And yeah, that's what we do.
Thanks. Yeah.
Okay. Great. So let's start with the first part of the talk, where I'll discuss like how we find the best strategy to B-cosify a model. So I'll give a very quick B-cos background, because I think it's kind of the base of how we calculate the explanations and stuff. But Definitely, I recommend to read this paper. It's an awesome paper by one of my co-author Moritz, and it's really well written, and you could see all the mathematical details. But just to get an quick idea of what are the main key points that are used in our work, let's talk about it. So first, let's talk how it brings the interpretability. So in general, a standard model has a linear transform, which can be written as the weight times input. And you could also extend it saying that the norm of the weights and the input into the cosine of it. So this is your standard linear transformation which you have. But in the B-cos case, what happens is that you could divide this cosine term further into the absolute value into the sign, which does not change anything. It's like another way to represent it. Specifically, what is done here is the cos power, the cos absolute power is raised to some value, which in turn have alignment pressure between the inputs and the weights. And the hope is that the weights would align to the input and to the features which are really relevant to a specific output. So that's how it's achieved. So you just try to reduce the angle between the inputs and weights, and also like they use normalized weights. It's more like on a scaling terms and some mathematical bounding factor, which I'll also discuss that ultimately we don't need it in our work. But yeah, just to give you an example here you could see how this the weight input alignment works. So as the B parameter is increased, the cosine power highs, and it tries to align the weights and inputs which are really relevant to a specific problem. So on a very high level, just remember this for now. Second part, so this is, yeah, that's what it's called, the align pressure. And in the second part, like how these models are shown to be faithful, again, like there is a concept which is called dynamic linearity, which is basically the output could be represented as the multiplication between the linear transform or the dynamic linear transform, which is input dependent, times the input. What does that mean? So given an input, you can simply take a cross product with the explanation, and you would literally get the value of the logic. And this is called dynamically linear because during inference, you could literally treat it as a piecewise linear function and calculate these explanations. So the whole model becomes a single linear transform, which could be summarized. So you could just get the output by multiplying these weight vectors, dynamic linear transforms into input, and you would get the logic scores. So on a very high level, like these are the two things just to remember, like how, because we'll see, like we also play with the B parameter to have a good explanations, and it's important to just have a quick idea. But definitely I would recommend to check out the paper. Okay, so now now we know, like on a very high level, how B-cos works, and we have an idea how the standard models usually are. So I would, in this first part, would take an example of a ResNet 18 architecture, because that's the simplest convolution model is there, and I'll one by one, step by step, try to explain and show like which different components made sense for us and how we brought interpretability to it. So let's talk about how the standard models and B-cos models differ. So in general, the standard model has 3 input channel, while the B-cos model takes a 6 input channel. And why is that the case? Because the 6 input channel enables it to have a colored explanation, which is unique for each input pixel. Similarly, like the standard models have convolution layers, the B-cos model use a B-cos convolution layer, which is again like is the same transform as we discussed before, but the B power is raised higher for a higher alignment pressure. Standard model use batch norm, because use something, it's same, but it's use batch norm uncentered, where they don't subtract the mean, and then this all, like because of the model faithfulness, it's required to do in such a way. Standard model uses activation layers such as ReLU, but in the B-cos model, it has shown that it doesn't require any activation. And they also have some ablations later on to show that, okay, you can also use something called max out activation, which is a generalization of ReLU, and it still works, which also we incorporate in our work. Further, standard models use max pool, but B-cos has average pool. And similarly, in these different layers have these changes accordingly. In the end, when you have this average pooling layer and a final linear layer. But in the B-cos model, they reverse this order.